Okay. So, so far we have looked at, so previously before this we looked at p-n junctions of forward bias, so we derived the diode equation with very simplistic assumptions. Now we are looking at in much more detail what happens under reverse bias, okay? And we went through the basic physics of what happens. So I won't review this part, but let's quickly review the breakdown physics, okay? Because they're important for our practical applications, as we will talk about today in the class as well. The first is the Zener breakdown. So there are two methods, two mechanisms for breakdown. First is a Zener breakdown, which happens at lower voltages. This has to do with electron or hole tunneling effect, quantum mechanical effect. The second is high voltage applications, which is what's an avalanche effect, very much like avalanche in the ski slopes and so on. We'll talk about that today. Okay. The Zener breakdown is what we talked about last week, and let me very quickly review it, because it's an important phenomena which is applied for a variety of circuits, which we'll talk about. So essentially, what is reverse breakdown? If a sufficient reverse bias voltage is applied, so first of all, let's make sure we understand. In an ideal diode, if you apply a forward bias, you get high current. If you apply a reverse bias, you get zero current. That's an ideal diode. In a real diode, which we have seen, when you apply a reverse bias, you get some current, some small amount of current, right? So if I were to draw the current voltage characteristics of a realistic diode, you see current going up exponentially with voltage, we know this, and current here being very small, okay, which is pretty much independent of voltage. This is what we know now. What we're going to say is that when you apply sufficient voltage, this can break down. Which means you can have very, very large current flowing here, which is at a fixed voltage, pretty much. So called the breakdown voltage. So so this regime is what we've seen so far. This regime is what we're going to talk about. Okay, so keep that perspective in mind. So first of all, that's what's shown here. So you see the reverse bias current here, forward bias current here. So the first question is, under forward bias, you know that the voltage across the junction is very small. Remember, it's basically contact voltage minus the applied voltage, V0 minus V. Okay, so this drop here is very small, which means that the current is basically determined by this resistor, right? Imagine that there is 0 volt drop, and the current is what? C over R, right? Under reverse bias, the situation is different. First of all, because you have this region here, which is voltage independent. So I can keep increasing the voltage here, and nothing happens to the current. So if nothing happens to the current, that means my voltage drop across the resistor is basically constant, right? The current is constant, pretty much. So the extra voltage that I apply has to go somewhere, right? I'm applying more and more. Say I apply 10 volts here. But the current is fixed. And the drop here, let's say, is whatever, 2 volts, okay? Based on the resistor and the current. Then the extra voltage has to drop somewhere, which is across the p-n junction. Which we know, right? Because that raises the band bending. It bends the band and you get the high voltage. Reverse bias. Okay, so you can basically have very high voltage. But at some point it breaks down and you get very large current. Okay? Then you have an intermediate situation when you have a large current flowing through the resistor, you'll have large voltage drop, and you also have reasonably large voltage across the junction. So your voltage drops across both the resistor and the junction. So this is the way you would actually treat a p-n junction diode in an actual circuit. Okay? It's not as simple as an ideal diode. An ideal diode is very straightforward, right? It's just a ones and zeros. In p-n junction, you have to worry about these regimes. So we're going to look at the reverse breakdown regime. Okay? Basically, an external resistor is used to limit this current to prevent the thermal destruction of the device, as I mentioned last time. The point is that this can be very large, right? This is current, so the reverse current can go very, very large, independent of the voltage. At a fixed voltage, you get very large current. The only way to limit this is by applying an external resistor. Right? When you apply an external resistor, then that will have a voltage drop, which will determine how much current will flow through it, basically. And since it's in series with the junction, that determines the whole current in the circuit. Okay, so make sure you keep that picture in mind. Okay, because when we go into the physics, you know, these things will become abstract, but keep that big picture of this simple circuit in mind. Okay, so of course, why are we studying this? Because there are devices which are used in reverse breakdown. So this is a little bit counterintuitive because one would imagine breakdown is a bad thing. You're destroying the junction. Not necessarily. Okay, there are very, very important applications where you actually use the diode under breakdown. So that's why we need to understand the physics of what this is. So I had a question here. What is the current here? That should be relatively straightforward now, right? But let's make sure we are all clear on this. So if I apply voltage, reverse biased, I have a resistor. Okay, I have a PN junction. So it's reverse biased, so my P is, sorry, N is here, E is here, so it's reverse biased. Okay, so if I apply voltage E, this is R, and the current flowing is this way, I. My voltage drop here is, let's say, VPR. For Ohm's law, you should be able to apply this, right? E equals E minus VPR over R. Right? This is applying Ohm's law. So you should be able, if you know resistor, you know apply voltage, you know the current, you can calculate like that, or you know one of these. Okay. Usually this thing is fixed, so it allows you to calculate the I. Okay. Now you can see if there is no R, what happens to the I? Let's say R is 0. Goes to infinity, right? And that's a problem. That's why you put an R in. You see that helps you to limit the current, right? But anyway, you should be able to keep that picture in mind as we keep going. Now the physics of how breakdown happens, like I said, there are two mechanisms. The first one, which is Zener Breakdown, this happens at low voltages. So the idea is that so this value here for Zener is small in the order of, say, 1 to 5 volts. Okay, and we'll talk about Avalanche, where this is 10 times, 100 times larger. Two different physical mechanisms. Okay, when we look first at the equilibrium band diagram to understand Zener breakdown. So we have a bent band here, you have P-type here, N-type here, and everything looks good. You apply voltage in reverse bias, of course the bands bend more, right? You're increasing the energy barrier for the carriers from going either way, right? Now, so let's see what happens. If you apply enough of a voltage, and this junction here is very sharp, okay, the PN junction is very sharp, and it's heavily doped, then this transition region W becomes small. Right? We understand that. It's heavily doped, transition region small. Then the voltage, so if you look at the junction, so that's our boundary. Let's say that's the transition region. That's W. Yep, of course, these are heavily doped, so there's no drop, right? No voltage drop there pretty much. We assume it's a perfect conductor. We know from last class, that this is not actually true. It needs to have some field, but for the sake of argument, that's very small. The field that gets applied here, which of course is in this direction, right? I'll be charges here, charges here, equal, balanced, and so on. This field is determined by the applied voltage divided by W, right? Pretty much. So applied voltage is what I apply. If W is small, this field is very high. Right? Smaller W, higher the field. Now, when the field is high, that means that this bands bend more as well, which of course is also determined by the applied voltage. Then, when the bands bend so much that the filled valence band on the P-type essentially coincides in energy with the empty conduction band on the N-type. Okay? Remember, in the simplified band diagram, the vertical axis is energy. Okay? The horizontal axis is location, position. But let's just look at in this close vicinity of the junction. You see in energy, the electrons here, which are in the valence band, which are trapped in a bond, are close in energy to empty states in the conduction band on the n-type. Okay? And the close in energy means that in principle they can tunnel through. This is very, very similar to the particle in a box that we saw before. Remember, we had a potential barrier which looks like that. And if we said that if we had a finite distance of the potential barrier, then whatever particle is in here, electron can tunnel across. We did a example problem for this, right? Now, of course, when the barrier is smaller this way, the probability of tunneling is higher. In our case, that distance is basically determined by this W. The smaller the W, so higher probability of this tunneling happening. Of course, also this energy barrier is smaller, you get a higher probability, but that you can't have much control over at this stage. Okay? So essentially what happens, you have lots of electrons in the valence band, which line up with lots of empty states in the conduction band. Electrons can tunnel across if this distance between them is small. Okay? Now, of course, if the electron tunnels this way from P to N, the current is the opposite way from N to P, which is the reverse bias current, right? Remember, the applied field is this way, the applied voltage is also in this direction, reverse bias, right? N type, P type, and this is the reverse bias current. Electrons go this way, current flows this way, reverse bias current. Of course, the same thing happens for holes. For holes, so let me see. For holes, it's a bit harder to explain, but it depends on where you look at the energy bands. But it's much easier to understand for the electrons. Okay? So the physical mechanism of why this happens is relatively simple to understand. Okay? If you look at the atoms in the vicinity of the junction here, the electrons, of course, in the valence band are held in the covalent bonds, right? So it's, imagine silicon has 4 electrons in the covalent bond. They're held very tightly. Now, the electrons in the vicinity of the junction will experience this very, very high field. Okay? Now, when you have a very high field, these electrons can basically be pulled out of the bonds. So the field can essentially break the bond. Okay? So the electrons here will get pulled out by this field. And once it gets pulled out, it's free and it's swept across by the field. Okay, that's a physical mechanism of Zener breakdown. Okay, this is essentially an ionization phenomenon. So the electrons in the covalent bonds of the atoms in the transition region are torn from their bonds by the high electric field and swept across to the entire region. And the field has to be quite high, so 10⁶ volts per centimeter. And of course, you can get the high field by reducing the W, right? Even at low voltage. So you see that. The W can be quite small if you have a sharp junction, right? It can be microns. Right? So that kind of field is not that hard to achieve if properly designed. So the one last thing to keep in mind is that this phenomenon is called the Zener effect, and we use this to regulate voltage, as you will see later. The idea here is that this allows you to fix the voltage when the breakdown happens, and you can control that voltage. So you can think about this essentially as a way to regulate voltage coming out. So let's say you need a very fixed voltage coming out. You can see that you can use something like this. I'm going to look at an example. Okay? So again, the requirements are you need a very sharp junction, you need heavy doping on both sides. So this is something you can design for, and you can control the voltage this way. Okay, W is small, under reverse bias, the fields are high. Okay, so the next breakdown mechanism is the avalanche breakdown. Avalanche breakdown is relatively simple to understand compared to the Zener breakdown. It's very straightforward. You have an electron coming in. Okay. First of all, the big difference with Zener breakdown is that this occurs at higher voltages. You need much higher voltages, and typically you don't need a very, very sharp junction or very high doping on both sides. So you can have a larger transition region on one side. Now, that's useful because most PN junctions tend to be heavily doped on one side with respect to the other. Okay, so you have P plus N or N plus P, which is because this has to do with the fabrication. You start with the N-type silicon wafer. and you very heavily dope it to make it P+, so you get the P+ N junction. Okay? So for practical reasons, many of the diodes that you can buy which are in breakdown turn out to be avalanche breakdown. Okay? But in any case, Zener breakdown is also important because of the lower voltages required. The principle of the physical mechanism of avalanche breakdown is very straightforward. You have an electric field. Okay, this happens in the junction. So you have an electron, which is shown in green, which is accelerated in the field. Of course, it goes in the opposite direction for the field, right? So it's going from right to left. Okay. Now, if the field is high enough, this electron can gain sufficient kinetic energy. Okay, that when it impacts another electron in a bond, it can kick it out of the bond. So you have one electron coming in at very high energy. It hits an electron which is bonded to silicon, so it's in the valence band, okay, and kick it out of the bond. So essentially, this electron can come in and break the bond. Okay. Now you see what has happened is that when you break the bond, you've created an extra electron and a hole. Okay. So in other words, you came in with one electron, you ended up with two electrons and a hole. So you multiplied the current, essentially. So you can see, if this process continues, you can have a multiplicative effect. So you can see an avalanche sort of effect. Okay, and there's a nice animation which kind of explains this. But let's look first at the energy bands. Again, from the band diagram perspective, the bands look exactly the same as the case of the Zener, except that now you see that the transition region is much wider. Okay, so the tunneling probability here is very small. So you have low tunnel current, but the electron that gets accelerated through the field has so much kinetic energy that it can hit an electron which is in the valence band, in the bond, and kick it up. Okay, you can kick it up to the conduction band. Of course, this extra energy that this electron gained from the field now is lost. Right? It's lost because it has been transferred to the other electron and the hole. So it goes down in energy a little bit. This electron goes up in energy, and you also create a hole which goes up in energy. Okay? So you came in with one electron, you ended up with 1, 2, 3 particles. So 1 became 3. So that's the multiplicative effect. So you see the current increasing also at the same voltage. Okay? Voltage is the same, nothing to do with the voltage, but current has gone up. Okay? So that's the physical mechanism. Now, of course, so in this electron collides with the lattice, you can break a bond and create electron-hole pairs. The original electron loses some energy, like I said, transfers it. As a result, two electrons in one hole crosses the junction, and the current has increased. Now, you can also, this is the carrier multiplication, but you can also have secondary carrier multiplication, tertiary carrier multiplication. In other words, the carriers that are generated can generate even more carriers. Right? The mechanism is exactly the same. So this is the one electron-hole pair. So you have electrons coming in. You have an impact ionization going on here. The hole goes this way. The two electrons go this way. Okay, that's what we just saw. But we can also have a situation where the electron comes in. You have an impact ionization here. An electron is created. Another hole is created. Now the electrons went away to the other side. But this hole now has also significant kinetic energy that it can also undergo an impact ionization, okay, and transfer energy to an electron in the covalent bond, again pull it out of the covalent bond. Okay, so it can create holes in electrons as well. So another electron goes this way, and this electron now can also undergo impact ionization, create more electron holes. So you can see this multiplicative effect, right? So you can see it's an avalanche sort of process. So you have one carrier coming in, okay, creating, it's another way to think about it is, you have one carrier coming in, it generates two more electrons and holes, and itself, right? And each of these can generate two more and themselves. Right? This is probably more because it may not have enough energy, and so on and so forth. So you can see this multiplicative effect. So it's like an avalanche. That's why it's called an avalanche breakdown. Let's see if I can open this. website that shows a really nice animation to understand this. So essentially, this is the same thing. You have a P-type material, N-type material, a large depletion region, so you can actually see what's going on. So let's say you inject an electron. Okay, they have a certain mobilities for the electrons and holes. You have a certain device length. You inject an electron comes in, you create a hole, and they have 2 electrons going out. Okay, so that's a simple ionization problem, and it's random. So sometimes it'll do more than one. So you have to kind of just do it a few times. They do a stochastic model, so this is exactly what happens. So you can see the avalanche process right there. So the created electrons and holes will create more. You can also do the same thing for the holes. The process is exactly the same. Of course, when the holes are traveling, remember it's basically the electrons hopping from bond to bond, right? So the physics is a little bit different, and their mobilities and the effective masses are a little bit different. But the idea is the same. Okay, so make sure you're clear on that.
What are alpha and beta in that example?
Say that again.
What are alpha and beta in that?
In that example, the mobilities
Okay.
for the electron in the hole. Okay, but you can read through the website. It's I posted it, so you can just copy it, read through it. It explains how they do the modeling and so on. It's basically stochastic, so it's a random model basically. Because these collisions happen with some random distribution. There's a probability that determines this collision, okay? Which allows us to quantify this a little bit with very simple models, okay? So to analyze this, we can do a very simplistic model where if you have n electrons coming in, okay, each electron will generate with the probability P, one impact ionization. Okay? So let's imagine this. One electron coming in. There's a probability P that this impact ionization happens. So, but after this impact ionization, what you have is 1 plus P carriers. Electrons. Okay? Plus 1 hole. You haven't considered the holes yet. Okay? The probability is P is, so one collision created 1 extra electron. Right? Ignore the holes for the time being, so only look at one of these. Okay, so if you have one collision event happen, you have 1 electron, which is the original electron plus another electron, so you have 2. But of course, the probability that the second electron is created is some P, some fraction. This is a random event, right? Now, of course, each of this can give rise to more collision events, which can be modeled as P times P. Right? First collision event multiplied by the second collision event, which is basically from the law of statistics, probability, you have 2 independent events. Okay, you get multiplied. 2 independent events happening, let's have one after the other. Okay? And so on and so forth. So you have 3 collisions and so on. You essentially have a geometric series. Okay, the simplistic way to model it. You can add them up and you get a very simple expression. So the total carriers crossing the junction is given by, it's determined by the probability that each carrier creates an electron-hole pair. And if we ignore recombination, so we ignore the fact that sometimes within the junction, because there are carriers, they can recombine. But if we ignore that, and that's a reasonable assumption to ignore it, because if you have a high enough field, it just gets swept across, right? Before they recombine, it just goes across. Then we can simply calculate the multiplication factor, which is how many electrons come out divided by how many electrons went in, as basically 1 over 1 minus P, just the sum of the geometric series. Okay? Now you can see as P increases, the probability that this ionization happens increases. The multiplicative factor can go up to infinity, right? So probability is between 0 and 1. If it goes to 1, 1 by 0, right, goes to infinity. So it's essentially an avalanche effect. Now, of course, one has to do much more complicated modeling to understand what determines this probability. Okay? Of course, we can make some simple guesses. If your band gap of the material is very large, the probability is lower. Why? Because the probability, so what probability are we talking about? We're talking about the fact that an electron came in and hit another electron which is in a bond, which is in the valence band, and excited it to the conduction band. The larger the band gap, the harder for it to be excited, right? So that's common sense. So the other thing, of course, is also the field, right? The larger the field, the higher the kinetic energy of the electron coming in. So higher the probability that it can be excited. Okay? Typically, the field is the only thing that you control once you've actually fabricated the device. So the calculation gives something like this. The probability goes as what V over VBR, which is the breakdown voltage raised to some n, and depends on the material and so on. Won't go into much detail, but make sure you understand the qualitatively what this means. Okay? The probability will depend upon the electric field and reverse bias voltage, and some empirical relation can be used. Again, the breakdown voltage also increases with the band gap and decreases with more doping. Now, the doping is an important consideration. Remember that in an N plus P junction, it's a little bit subtle, but okay, sorry, P plus N junction, the depletion region is small, depletion here is large. Now, if this distance is very large, the applied field will be small, right? Which means that the excess kinetic energy that the electrons have gained is small as well. So in order to increase the probability that this impactonization happens and creates an electron pair, you want to make this smaller. Okay? In other words, you want to increase this doping. It's another way to control it. Okay? Of course, ideally you want both of them to be very highly doped, but sometimes you have some constraints on how much you can put in to start with, because you start with an N-type silicon. Okay? Now, what are these used for? So first of all, you can see a simple example is shown here, and we'll look at this in some detail. Imagine that you have a voltage coming in which has some ripple on it. Okay? This is very common. For instance, if you plug into your outlet, and of course that's AC. Okay? But let's say you have a simple rectifier which converts AC to DC. But typically, cheap rectifiers will never be flat, right? You'll always have some ripple, which I assume you have learned in your previous circuits class. Okay. Yeah. So if you recall, in your AC to DC converter, it is never flat. Okay. In fact, we will actually look at rectifiers later on, so we will actually revisit that. But you'll always have some ripple going on top of it, and this just has to do with the capacitive response of your circuit, the LCR response, if you go through it carefully. In any case, so what you get is some sort of voltage here, which has a DC value bias, and then you have some ripple which runs on it. But in some circuits, for instance, if you have a very sensitive circuit like a CPU, for instance, right, you want your transistor to be pretty much at switching between, say, 0, minus 1.5, 1.5, whatever it is that you design for. You want that to be rock solid. You don't want any glitches there, because if you have a small glitch there, that can change the current in your transistor, and that can mess up your logic. Okay, and that can really be bad for digital logic, right? So, because in digital logic, you want 1 and 0, basically. You don't want anything in between. So you want to end up with something like that. Okay? Let's say rock solid like that. And you can do that with this very simple circuit as shown here, which basically has a resistor and a breakdown diode. And the nice thing is that in the breakdown diode, the voltage is essentially fixed by the materials, right? Whatever you decide in your junction. You're doping, basically you're doping. Okay? Of course, it will also depend on your voltage ranges and so on, but you can design for it. Okay? So you have a very fixed voltage drop that comes across here independent of the current. So even though you have a big varying voltage coming in, your voltage coming out is basically rock solid. So that's a very important application of these. Now, of course, you can do the same thing with other devices, which are typically vacuum tubes, or there's also variable resistors and things like that. But those are all discrete components, and they're very slow. Okay, this is completely integrated. In other words, you can put this on a chip. Okay, which is very important, first of all. Second, it can be extremely fast. This is picoseconds, 10 raised to minus 18 seconds or so. Fastest response you can get. So you can get rid of very, very fast varying signals, which is impossible to do when you do vacuum electronics or other older discrete devices. Okay, so that's why this breakdown diodes turn out to be quite important practically. Okay? So again, just to emphasize this, one can control the doping and the sharpness of the p-n junction. How sharp is it? In other words, how small is this? That allows you to essentially design any kind of breakdown voltage that you want, okay, with a very specific breakdown voltage. And the reverse bias current will be independent of breakdown voltage. So basically, this would be exactly at minus 15 volts as shown here. Okay. So one interesting point here is that these diodes, if you buy them, they're all called Zener diodes, even though most likely the mechanism is avalanche breakdown. Okay. Typically, it's avalanche breakdown because it's very hard to get the N plus P plus, very, very high doping on both sides to Zener. But you can buy them as well. But they're all called Zener diodes, so just don't be confused if you actually see any of this. An application of such a breakdown diode is a voltage regulation, as we just talked about. Of course, you can also use these as reference voltages, right? So let's say you have some in a digital logic, you want to, if you're above some voltage, you want something to happen. You're below voltage, you want something else to happen. And that voltage has to be rock solid as well. That can be a reference voltage, and you can use something like this for that as well. Not just for voltage regulation, you can use it as a reference as well. Essentially, is determined by the fabrication of your device. And another important application, as I mentioned before, is ultra-first surge protectors. So if you want to prevent very large voltage spikes in very, very sensitive circuits, and very large voltage spikes coming in very fast. It's important, for instance, for not just for digital logic, but also for power conversion, but very specific cases of power conversion. I can't think of some examples, but they'll come back to me. I forget now, but they can be very fast, so you can have this response rock solid. Now, the speed of the response is what we will talk about next. So we will look at this in detail because that turns out to be a very important characteristic for the practical application of these devices. Okay? So the speed of the response, of course, is determined by the non-equilibrium situation, right? You have voltage that's applied, and then you switch the voltage to the other side. So what happens for the physics of these semiconductors? We need to understand that because that's what limits the switching speed. Ideally, you want this to be instantaneous, but we know it cannot be instantaneous because charges have to move, okay? And that takes time. That takes diffusion time. We know this, so we expect that, right? Okay, so again, going back to this, if I apply a voltage very quickly this way, you cannot expect that this will be an instantaneous change, right? You can see there's a small shape here. That's small, but it's still there. We need to understand where that comes from. Okay, that's the picture. So far we have looked at p-n junctions as steady state, but most such devices are used under AC, for voltage regulation or for switching. So we need to have some basic understanding of how they behave transiently. Now, the actual modeling of these devices is typically done numerically. You have to solve partial differential equations in space and time, and it turns out to be complicated. But we can gain intuition by making some simple approximations. For our level of understanding, it's much more important that we gain qualitative intuition. Okay, so that's our goal here. So let's look at the switching of a diode from forward to reverse bias in detail. So we're going to look at a very simple situation. You have a forward bias diode, and you instantaneously switch the voltage to reverse bias. Okay? Let's see what happens. The physics is relatively simple to understand. So when we have forward bias, first of all, let's recall what happens. Okay, under steady state carrier injection, we have a charge distribution which looks like this. So we have a P. So first of all, in this diagram, which one is more heavily doped? Right, it's an N plus P because the depletion region on the N side is smaller than the P. Okay, so when you apply forward bias, of course, our picture we saw before is essentially the holes from here, the majority carriers get injected across the junction, and then become minority carriers, and then they diffuse. Okay, that's the mechanism for the current. Okay, they create a distribution which looks like this. This is a steady state distribution because you have recombination happening, diffusion happening, carrier injection happening. All these things basically balance each other to create a steady state distribution. Okay, we saw this before. You should be fairly clear about this. In fact, you should be clear about this for the midterm. Okay, because it's steady state. Should be straightforward. Now, of course, with the electrons, the same thing happens. The majority carriers here get injected across the junction, and then they diffuse. Okay, they create a steady state distribution which looks like that. Now, of course, because you have a concentration gradient, the electrons are diffusing from right to left. As they diffuse, they also recombine with, because there's lots of hole sets, a p-type material, they will recombine, right? So, but at the same time, you have this recombination and diffusion is balanced by the carrier injection. So you have a steady state distribution. Okay? This is equilibrium. Okay? Now, of course, what we are saying is that the current changes, right? You're basically turning off, on and off a diode, basically, right? So the current is changing instantaneously. Okay? So you can either control the current or voltage. I mentioned before voltage, but now we're going to talk about current. So let's say I just turn off the circuit. Okay, the current has changed instantaneously, going from some high value to 0, basically, right? If I just turn off the circuit. But the charges cannot change instantaneously. The charges always have to take some time. They have to diffuse. They have to go away somehow, or they have to recombine, right? That takes time. It's not instantaneous. Which means that the voltage will lag behind the current. This is nothing but a capacitor. Same thing happens in a capacitor, right? You have a charge stored, it needs to be discharged. It takes some time. Remember LC, time constant, all that stuff from your circuits, it's the exact same thing. The physics is different, but at the circuit level it's exactly the same thing. Okay? Now we're going to understand the physics in a bit more detail. So first, the current changes, we can expect the charges to change as well. But it takes time for the charges to change. In other words, charges will lag the current. This is the capacitive effect of the p-n junction. Okay? So again, keep that picture in mind. First of all, make sure you remember we're talking about this switching. Okay? Not just this regime, but the whole switching. We're going to go from here to here to here. Or in current. Okay? We're going to go from very large current to zero current to negative current. So keep that picture in mind. Okay, and then we'll look at the physics of what happens. Okay, to solve the problem mathematically, like I said, we have to make some assumptions, but let's start with what we know. What we know is a continuity equation, right? So which we looked at before. Essentially what I said just now, if you look on either side of the junction, you have three things happening, okay? The carriers are diffusing. They're going from high concentration to low concentration. Electrons or holes, it doesn't matter, depending on which side you are. They are recombining. Okay, electrons are recombining with holes. Holes are recombining with electrons. Okay. The third thing is that carriers are being injected, or not. If it's reverse bias, they're not injected. But if it's forward bias, they're injected. There are only three things happening. Okay. So you can model it. So we saw this before from chapter 4. The concentration, rate of change of concentration of holes. Now, remember the hole concentration is a function of position, because remember there's that diffusion happening. Function of time. The rate of change of concentration as a function of time is basically that. Because just to remember our notation, P, function of x and T, P naught. Okay, this is a constant basically, plus delta P. This is our notation. This is basically the equilibrium. Okay, no. So the time derivative of this is basically the time derivative of that. That's just the excess carriers. Now, that's the left-hand side. Now the right-hand side is what I said. This term is very simple. It's just the recombination term. Right? Recombination is proportional to the recombination probability, which is basically inversely proportional to the lifetime. Okay, 1 over tau p. Of course, it's also proportional to the number of carriers that are there. Okay, recombination probability depends on how many carriers are there to recombine, divided by the lifetime of the carriers. Okay, so that's that term. It's a negative sign because it's getting rid of the carriers. Right? So it's negative. It's decreasing the carrier concentration. This side is the carrier injection current. Okay? But this is the diffusion current. Not just the carrier injection, this is also the diffusion current. You can think of this side as a carrier injection, but we'll come back to that. Okay, this is just the diffusion current because it depends on the concentration gradient. Okay? We derived this by looking at a slab of a semiconductor with a small region where you have current coming in, current going out, and recombination happening. Okay, so go back and review that. But basically, we derived this. The same thing for electrons. Pretty much the same equation, except that now the charge of the current are different. Because electronic charge is negative, so the current is the opposite. Now, of course, to solve this equation, we have to solve this in both time and space. Okay, so if you recast that equation, okay, this is the current, whole current. It's a function of space and time. Its space derivative is given by this term, which is the recombination term, plus the injection term, essentially. This is what I meant by the total rate of change of charge carriers. Okay? This is what's getting injected from the inside, pretty much. So to calculate the current density at any point, we have to integrate this equation. Okay? So any instant of time. So if you integrate this equation over from x equals 0 to some arbitrary value of x, you get jp of 0 minus jp of x, and this integral of this term right here. Okay, 0 to x of this term. Now, of course, that's complicated to solve, primarily because these terms in time can be complicated. We don't quite know what that is yet. Okay, but make sure you follow the logic so far. Okay, and we'll make some assumptions as to the time dependence soon. Now, as I said before, the assumptions are relatively straightforward. First, we assume that the current injection is from a highly doped region, which is usually primarily the primary component of the current, to the n type, so P plus to n. And we assume that the n is very long region. Basically, that assumption is that the diffusion current dies out at large values of distance away from the junction, which is also a reasonable assumption because the diffusion length is typically small, in the order of a few microns or tens of microns. So when you say long, this means it can be 100 microns. This can be very long. Okay, so basically that means that the total current is mostly whole current at xn equals 0. This is basically the assumption we had last time. If you have a P plus N junction, most of the current, so this is xn, right? Xn equals 0, xn. Most of the current here is basically the whole injection. Right? Because the electron injection here is small. It's mostly because of the P plus. Okay? This is what we saw last class. Now, then basically the total current is, of course, given the whole current plus the electron current. We make the assumption that this is mostly the whole current. So we just calculate the whole current. Okay? Of course, also we make the assumption that far away from the junction, the diffusion current essentially drops off to 0, which is a reasonable assumption, like I said, if you are a few diffusion lengths away from the junction. Current basically goes away because all the carriers are basically recombined. Okay? That's basically this part. Jp at xn going to infinity is 0. Okay? Then we can relatively easily solve the total current. The total current now is given by the whole current at the junction, at the boundary here between the n-type and junction, n-type and the depletion region. Okay, xn equals 0 as a function of time is now given by essentially this equation multiplied by the area, cross-sectional area. Current density times area gives you current. Okay, which is rewritten here, QA over tau p. This integral plus QA times partial derivative with respect to time of this integral. Okay? Now, it's like I said, this equation is hard to solve because we don't know exactly what the time dependence is. It is complicated. We don't know quite what that is yet. But we can understand this physically, okay, by looking at these terms. So let's first of all think about the first term here. Okay, if you look at this, what does this say? This is at some instant of time. This is essentially adding up all the excess carriers on the n side. Right? Which is integrating all the excess carriers on the n side. Times Q times A divided by tau P. But times Q times the excess number of excess carriers is essentially the excess charge on the n side. Okay? So this is the excess charge stored multiplied by A will give you the total charge stored on the n side, which of course recombines and disappears within its lifetime. Okay, so again, go back to our picture. The holes are injected from the P plus to the n type, they diffuse, recombine, and disappear. So the first term here represents the total charge here divided by the lifetime of the holes there. Okay, remember, within one lifetime, all these charges disappear and have to be replenished by the current that is injected. Okay, so you can physically think about this term, total charge divided by the time it needs to be replenished. Total charge divided by time, of course, is the average current. Okay, these are the charges that are basically disappearing every tau p seconds. And they need to be replenished from the other side. Okay, so it's reasonable to expect. We need to provide that current. Right? Okay, this is the recombination term. Excess carriers need to be replenished. Now this term is less intuitive. Okay? This term, if we look here, is essentially also, this integral is also the total charge, the same integral, right? The total, same thing. So it's a total charge. But now we're looking at the rate of change of the total charge, which is the part we don't know so far. Okay? We know that there is some change happening because it's a transient, but we don't know what it is quite yet. Okay? So that's the charge buildup or charge depletion term. Of course, in the steady state, that's zero. So this is the familiar equation that we had last time. The current is basically the total charge on one side divided by its lifetime. Okay? So try to understand this physically, not the math so much. Okay. Like I said, this is a little bit harder to understand. We'll look at that in a bit more detail for a very specific example. Okay, so first of all, the point to remember is that these equations, of course, cannot typically be solved by hand. They have to be solved numerically. And there are lots and lots of commercial pieces of software like Spice, or there's all kinds of different things that are used to solve these. And I believe some of you will probably use these in some of your advanced classes if you choose to. Okay, but again, the purpose here is to gain some intuition, some understanding from the equations. So we will take a very simple example and try to solve it and try to gain some understanding of what might be happening. Okay, so let's look at a very specific example. Again, if you think about this equation, first of all, you need to have some boundary conditions to solve it. You need to understand how the delta P looks like at different locations and at different instances of time. And then you can plug them in and solve them numerically or whatever, right? Now, if those boundary conditions are simple, then you can solve them by hand, which is what we will do in this example. Okay? The example is very simple. Essentially, we are controlling current. Okay? Just look here for the time being. It's essentially a current step function. You have forward bias, so you have some fixed current, which means you have a fixed voltage. And very quick, suddenly you switch it off. Okay? So imagine a circuit like this we saw. Okay? But now, where's the... So imagine a circuit like that, but it's of course forward bias. So imagine this, and imagine a switch. Okay. So the switch is closed, so you have some current flowing. Of course, the current is also flowing the opposite way. Okay. And then very quickly you suddenly open the switch. The current has gone from some fixed value to zero. That's instantaneous, right? Because you turn on and off the switch. In principle, that can be instantaneous. There's nothing wrong with that. But, of course, if you look at the charges, that cannot be instantaneous. We know it has to have some lag. Okay? Which means that the voltage also has to have some lag. So the question we are trying to answer is, in a situation like this, what is the current voltage characteristics? What does the voltage look like when we have switched off the current? That's what we're trying to answer. Okay? Essentially, what is going on in the transients here? Okay, so in this situation, if you look at the current voltage curve, we are at some fixed voltage or fixed current. Suddenly, the current goes to 0. How does the voltage go down? At some point, it has to go to some fixed value. So we need to understand how that voltage changes. Okay, so it takes some time for the excess holes to recombine with the electrons and the total charge to go to 0. That's the physics. Okay, so we know that a carrier distribution, which so it's a P plus N junction, okay, P plus N, and we know the carrier distribution looks like an exponential decay in space. So at an instant of time. So look at this blue curve. Okay, that's t equals 0. That's what the excess holes on the N-type look like at that instant of time. Okay? Now the question is, how do they change with time? And of course, we know they have to go down because they recombine. Right? So remember again, the physics is that you don't have carrier injection because you turned off the current. So the only thing the carriers can do now is diffuse and recombine. Okay? So that's what will happen. And they'll go away. In fact, that's what you see. You see that the peak goes down because it's diffusing away from the peak and also recombining with lots of electrons there. It's an N-type material, remember. Lots and lots of electrons hanging around. So, of course, to solve this equation, it's a bit more complicated. We use a Laplace transform in this case because you have to solve this differential equation. Okay? This one or this one, same thing. Okay? But we're going to solve it in charges, so it's basically the Laplace transform. So you get a Laplace variable S, which of course is related to time. Now, if you don't remember Laplace transforms, go back and look at the video that I posted online. There's a short tutorial there from Cindy First, actually. It's pretty good, so take a look at it. But it's pretty straightforward. Remember, when you take derivatives, you multiply by S, you take integrals, you divide by S. And then you have to worry about the boundary conditions and so on. But basically, it's as simple as that. Okay, so the equation looks something like this. This is the QP over S is basically the first term, the recombination term. Okay, total charge divided by the lifetime, not much to it. This term is the derivative term. Because of the derivative, you get an S there. Okay, and that's the initial charge, I times tau P. Now remember, I is the total current that was going across at that instant of time that we were applying, that fixed current. Times tau P, of course, the total stored charge, because tau P is the recombination lifetime. Right? So that's pretty simple to understand. Now we have that's our initial condition, by the way, right? That's our t equals 0 condition. So you apply this equation and you solve it, you get a fairly straightforward expression like that, and you do the inverse Laplace transform. For 1 over 1 plus s is basically e raised to 1 over s, right? It just comes from the integral. Anyway, that's the inverse Laplace transform. I won't go through the basic stuff here, but you get an expression which looks like that. So what this is saying is that the charge, as a function of time, is dependent on the initial charge, which is I times tau P, times an exponential decay term. Okay? And of course, the exponential decay term depends on the lifetime. It decays as a function of the recombination lifetime. It's expected. This is what you expect. Now, why has the diffusion term disappeared? Any thoughts? I mentioned before that, of course, you have a concentration gradient. You should also have diffusion. So the point is that this is an open circuit, right? No current can flow. So that prevents any diffusion current as well, right? Remember, we turn this off basically, right? You cannot have any current. Basically. The only thing that happens in diffusion is recombination. So it's a simple problem to solve. Okay? So of course, you expect the total charges to decay with time, so you get an exponential decay as shown here. So this is time. You start off with lots of charges stored. This is the entire charges on the n side, and over time it decays because they're recombining with all the electrons. These are holes, remember. Okay? And in terms of the carrier distribution, on the n-type, you see it's a complicated function. That turns out to be much more harder to solve, the distribution of what the charges look like. But we can expect some sort of decrease like that and spreading out. Okay? Not so much spreading out. Forgive me. That's not quite right because there's no diffusion happening. There's no current, right? Okay. Now, again, the goal here was to understand how the voltage changes, because we are trying to understand the switching characteristics. Okay? How fast or how slowly does the voltage change? Of course, we have to calculate the voltage by looking at the distribution of the carriers, right? Because we have a very simple expression which relates the carrier distribution to the voltage across the junction. Okay? This is something we derived before. So again, even though the current is turned off, the charge and hence the potential persists across the junction. Okay? It lags behind the current. Okay? This, of course, is difficult to solve, like I said before. And this is the time-dependent potential, which we are trying to solve for. Okay? Now we have to make some assumptions, like I said, because we don't know really how the delta Pn changes. Now the assumption is a very common assumption we'll actually make in lots and lots of devices. So let's try to understand this conceptually. It's what's called a quasi-steady state approximation. Okay? So we will assume that it has some steady state properties, but it's really not steady state. It's a transient. Something is changing, right? It's not really steady state. So and we will apply this in many different situations, so we'll come back to this. But the assumption here is fairly simple, is that we will assume that the distribution of carriers is exponential. Now there's a fundamental problem with this assumption. Okay, and I'll come to that once we've gone through this model first. Okay, so we'll make the assumption that the distribution of carriers is exponential, and it's a reasonable assumption to make. Why? Because at the starting point we know it's exponential, right? We know that it looks like this, right? We solve the continuity equation, we got this expression. So it's a reasonable assumption to make. Okay, and it will remain exponential. That's the assumption we're making as it changes in time. Not strictly true. I'll come back to that. Okay. Now, if we make this assumption, then this equation becomes very simple. You can plug that in here. Okay, and then you can calculate V. Inverse this equation, you get V. Right. So, but of course, we can also plug it into this solution that we found. Okay, because then we can relate it to the lifetime and to the current, because remember we're trying to get voltage-current relationships. Now, so if we do that, you plug that in, do the integral over xn. This is an exponential, so it's pretty simple to do the integral. You get something like that. Okay. Now, of course, if you look at this, that's just the total excess carriers at xn equals 0 at the interface. Okay, and you have these terms here. Now, this also tells you that the excess carriers is now related to the charge divided by QA times the diffusion length, which is also intuitive if you think about it, because A times the diffusion length is the average volume that these carriers exist in. And Q is just the electronic charge. So total charge divided by Q is just the number of carriers. Number of carriers divided by the average volume they exist in is the average concentration. Yeah, so it kind of makes intuitive sense. Although, I'm hand-waving here a little bit because we made this assumption of this exponential. Okay, then the voltage, then you can take this expression, plug it in here, and invert this equation to get the voltage. So it's pretty straightforward. Kh over Q, some logarithmic factor. Okay, now you see that the transient in voltage is complicated. Okay, it has this logarithmic expression. Of course, we also have this exponential term, so it's a fairly complicated relationship. So this simple model essentially tells us that Of course, first of all, you see a time dependence here. You have an exponential time dependence here, which is within a logarithm. So it's not a simplistic exponential. So exponential can be fast, but it's not just that. So it's exponential within a logarithm. So it can be slow, which is a problem, right? You want these things to switch fast. So it is, voltage cannot instantaneously switch in a p-n junction diode due to the excess stored charge. If you use a highly doped P plus N junction with the N region smaller than the whole diffusion length, so what does that mean? If this region, which is in the N side, is smaller than the whole diffusion length, then this recombination can happen really fast. That's what it means. Then very little charge is stored, because this distance is small. Okay, that integral 0 to x is smaller. Lower charge is stored. Of course, less charge is stored, faster it is to discharge it or recombine, essentially. So you can make it faster. Okay, and this particular device is called a narrow base diode. The base is the N-type material, and it's made very small. This is a very specific example. Okay. Also, one can also add impurities to increase recombination so the charges are dissipated faster during the switching. That's another way to think about it. Remember, what are we trying to do here? The charges that are there need to disappear. They need to disappear fast. So one way to do it is increase the recombination. One way to increase recombination is to provide impurities, which I don't know if you remember. Impurities create energy levels within the band cap. Then impurities will create some bands inside, which allows an electron here to essentially come down, a hole here essentially, and fill a hole here. It increases the probability of this recombination event happening. This hole, this electron, basically combined. Okay? So you can do all kinds of tricks like that. Now, coming back to what I said before, that this approximation is not strictly true. This has to do with the boundary conditions. So if you look carefully at this boundary, this gradient here, so first of all, remember the diffusion current is proportional to that. Okay? So at the junction, my diffusion current has to be 0, because I've turned it off. Which means at the junction, the slope here must go to 0. Now, that can happen instantaneously in a very small region, because you have a very minuscule amount of charges, and that can change instantaneously. That's okay. That doesn't violate anything. But of course, it cannot happen outside, far away. You have lots and lots of charges. Which means that it cannot be strictly exponential. You need to have some slope here, right? If this is 0, that means it's not an exponential anymore, right? So it's much more complicated. That's what I meant by this approximation. It's not strictly true. Okay, so it's not a purely exponential function. In any case, we'll actually come back to that also, like I said, with respect to the quasi-steady state. Okay, we have a few minutes. Actually, I think I will stop here. And if you have more questions, if not, I can continue going. But since we have 5 minutes, I wanted to leave some time if you wanted me to discuss any problem sets. Questions, if you have any specific questions from the problem set you want me to go through in the last 5 minutes, or if you have any concepts that you want me to clarify, let me know. This will be the last time we talk before the midterm. So I will stop here, actually. 3.4.